Okay, in the last lecture we talked about perceptron. We learned how to train perceptron. And okay, and today we learn about feed-forward neural network. So feed-forward neural network is basically some perceptron in different layers connected to each other. So you have, suppose you have a d-dimensional data. So x1 to xd represent a vector x, which is d-dimensional. Then you have a couple of perceptron, and you can have many of them in one layer. And you can add as many layers as you want of perceptrons. And the number of perceptrons in these layers don't need to be the same. So you have some layers of this perceptron, and at the end, for the output, either you have only one single perceptron or, again, a couple of perceptrons. So if you remember, each perceptron basically has two parts, or there's two functions. The first part is a weighted sum of inputs, right? And the second part is applying a nonlinearity on this weighted sum. So here, basically, this would be a weighted sum of the inputs, and suppose that I put this weights here. And then a nonlinearity, let's call it A. And a nonlinearity will be applied to this A, and that would be the output of this perceptron. So each of these perceptron does the same thing for this input data. So compute a weighted sum, but different weighted sums because they have different weights. And then they apply a nonlinearity to the function, and they have outputs. The outputs goes to perceptrons of the second layer. And so on, up to the end. And each of these edges have a weight, which basically, yes. I can't hear you, sorry.
You know how in every single column we have a certain number of circles?
Number of circles?
Yeah, like the perceptron.
Okay.
Is it at first are there D and then D minus 1?
No. The first one is D because you have d-dimensional input. Okay? So your input is a vector in RD, so you have d-dimensional input. So this d-dimensional input is a vector of x1 to xd. And that would be the input of your network. Okay? This is called input layer. Here you have D nodes that doesn't do anything except that feeding the values of this vector to the network, right? From now on, it's up to you. How many nodes do you have? You're going to select. There is no restriction or rule about it. So this is called input layer. This is called output layer. And any layer between input and output layer is called hidden layer. And we may have one hidden layer, we may have 10 hidden layers, we may have many hidden layers. It's up to you how you design your network. Okay, this is called feed-forward neural network. I think it's clear what's going to happen. You know, you have input, and this input weighted sum of these weights will be applied, and the nonlinearity will be applied, and the output of this, the first layer, would be the input of the second layer, and the output of the second layer would be the input of the third layer. Up to the end, that there's another perceptron at the end that take the weighted sum of the perceptrons of the, the layer before output layer and apply a nonlinearity, and that would be our output. Okay? So it's just a combination of perceptrons. It's called feed-forward neural network. Okay. So I told you when I was talking about the history of perceptron and neural network that one of the main problems for people was that they didn't know how to train these models, Even it was not easy at the beginning how to train a single perceptron, but when you have many perceptrons together, it's not trivial to train it. It's not trivial to optimize weights. And at the beginning, they used to just connect perceptrons randomly and set the weights randomly and change it until they get some good result. And there was no clear way of training. So a good way of training was proposed by many researchers. And now, actually, many researchers claims that this algorithm trace back to their work. It's called backpropagation. It has been, and it is today, the main algorithm for training neural networks, feed-forward neural networks, and convolutional neural networks, and RNN, and other type of neural networks. That's the main algorithm, backpropagation. So here we have a cost function as usual. So this cost function could be anything. For example, could be y minus y hat, when y hat is what the network generates, and y is the true value, and you want to see how far they are. Okay. Could be any other type of objective function that you think is appropriate for your task. And our job is to take derivatives similar to what we did for perceptron, that we took derivative of the output with respect to parameters of the model. The parameters of the model now are these weights, right? Optimizing the model means optimizing these weights. So I need a way to take derivative of this output with respect to these weights. If I can take derivative of the output, objective function, with respect to these weights, then I'm done. Because then I can do gradient descent, right? I can start with some initial value, and in the direction of gradient, I can correct myself until it converges, similar to the thing that I did for perceptron. But for perceptron, it was quite easy to compute the derivative. It doesn't seem to be a trivial job to take the derivative of this cost function with respect to one of these weights. And that's actually what backpropagation does. Backpropagation is a way to compute this derivative with respect to one of these weights. Okay, let's look at backpropagation and how this derivative can be calculated more closely. Suppose that I'm just looking at a snapshot of this neural network, and I assume that there is a layer L, and there is layer I, and there's layer J. And I look at one perceptron here, one perceptron here, and one perceptron here. I divide each of these perceptrons to two parts. I call the first part A, and the second part Z. And Z is basically A when a nonlinearity is applied to. So basically ZL is a nonlinearity applied to AL. And this nonlinearity could be a logistic function, for example. That could be the nonlinearity. It could have many different forms. It could be a hyperbolic function and many other type of functions. So this weight, I will call it UIL. So this weight is UJI, and this has AI and ZI, and this has AJ and ZJ. And there are many of these perceptrons in each layer. Okay? In each of these A's is basically a linear sum, weighted sum, of the output of the previous layer, right? So AI, for example, would be summation of all UILs times ZL over all of these L's, right? A weighted sum of these values. Okay, so what I want to do is to take derivative of the cost function with respect to one of these weights. So I want to take derivative of E with respect to UIL. Backpropagation is basically chain rule, you know. It's a wise algorithm, but mathematically it's just chain rule. So I want to take derivative of E with respect to UIL. I write it as derivative of E with respect to AI times derivative of AI with respect to UIL. Okay, what is derivative of AI with respect to UIL? You know, AI is weighted sum of these values. Means each Z has been multiplied to its corresponding weight. Add them up, it makes you AI. So AI is this weight times ZL plus this weight times ZL plus this weight times ZL. I'm taking derivative of this with respect to this particular weight. It's ZL, right? It's clear here. If I take derivative of AI with respect to UIL, it's going to be ZL. Okay? So basically this second part is just ZL. What about the first part, derivative of E with respect to AI? It's not clear what derivative of E with respect to AI is because there are many layers here, and I'm taking derivative of the output cost function with respect to one of the nodes, which could be pretty far from the output. So it's not quite clear what this value is. Let me call it delta I. So far I know that derivative of the output, the cost function with respect to one of the weights is this quantity delta I that I don't know what that is, times ZL, which I know. But this delta I is unknown. If I can compute delta I, I'm done. Okay? So delta I, which is derivative of E with respect to AI, I can apply chain rule again and write it as derivative of E with respect to AJ times derivative of AJ with respect to AI. Okay? Is that right? It's not quite right. I need to make a small change here to make it right. Do you know what that is? Just think about the concept of derivative. You know, I'm perturbing AI. If I'm perturbing AI, you know, I'm trying to write it in terms of AJ. If I'm perturbing AI, I'm changing this AJ, I'm changing this one, I'm changing this one, I'm changing all of them, not only one of them, right? So basically, I need a summation here. That's summation over all values of the layer J, because perturbing AI will change all of these values, all of AIs. Okay, derivative of E with respect to AJ, I had derivative of E with respect to AI, which was unknown. I call it delta I. Now I have it with respect to AJ. It is unknown again. I just call it delta J. Then I have derivative of AJ with respect to AI. AJ with respect to AI. I can write it as AJ with respect to ZI, ZI with respect to AI. So this term, I will write it as AI with respect to, you know, it's AJ with respect to AI. I will write it as AJ with respect to ZI, and then ZI with respect to AI. Okay. So delta I is summation over J of delta J, which is unknown, derivative of AI with respect to ZI. AI with respect to ZI, and then, sorry? AJ. AJ with respect to ZI, and then ZI with respect to AI. So AJ with respect to ZI, what is it? Derivative of AJ with respect to ZI. Sorry? It's just UJI, right? Don't forget the definition of A. Or just look at it, you know. Basically, the question is that if I perturb ZI, how AJ will change. So if I perturb this AJ, the value of AJ is a linear combination of all of these weights times all of these outputs. So I'm perturbing one of these outputs. So it will change by the value of this weight, right? So it's UJI. So this term is UJI. So what's the derivative of ZI with respect to AI? What is Z? Z is a nonlinear function applied to A. So ZI is basically some sigma A. I. Now I'm taking derivative of sigma AI with respect to AI, right? So it depends on the form of sigma. So that will be the derivative of sigma, right? So this last term is derivative of sigma at point AI. Is that clear? Is any question here? Okay. You know, this sigma prime AI has nothing to do with this, J. So I can take it out of the summation. I can write it sigma prime AI summation over J of delta J UJI. And this is delta I. This is key to backpropagation algorithm. You know, delta I was unknown. But I managed to compute delta I in terms of delta J, which is also unknown. But it's a recursive formula. So I can compute delta J in terms of delta K. And so on. You know, I can compute each delta based on the delta of the next layer. But what's going to happen if I get to the last layer? You know, each delta can be computed by the delta of the next layer. So suppose I do this recursively and I get to the last layer. What would happen in the last layer? In the last layer, again, I have a perceptron, and that would be the y hat, right? So without lose of generality, I suppose that, you know, I add another point here, which just return y hat. It doesn't do anything. It doesn't have any nonlinearity. Okay. A comes here and goes out. Or say y hat comes in and goes out. So suppose that's my last layer. My last layer is just the output. Okay? So at the last layer, I would like to take derivative of E. By definition, delta is derivative of E with respect to A. You know, derivative of output with respect to A. I added a note here that A and, you know, there is no nonlinearity. You know, this is A, and there is no nonlinearity here. So it is A, which is basically the output. So if the last layer is K, at the last layer, suppose the name is K, then delta K would be derivative of E with respect to A, K, which is basically derivative of A with respect to y hat. And this I can compute. You know, for example, if my E is y minus y hat squared, then I can take derivative of this with respect to y hat. It is simply 2 or negative 2 y minus y hat. Okay? So I can compute this derivative at the last layer. I can compute delta at the last layer. And that was recursive. You know, each layer depends on the next layer. I can go up to the last layer, compute it, and propagate back. You know, I have delta K, which is last layer. So if I use this formula, I can compute delta in the previous layer, and then compute delta in the previous layer, and so on. And then eventually I can compute derivative of E with respect to UIL. So backpropagation works this way. In the first step, you choose some random weights for the network. You feed data point to the network. It's clear that when you have some weights here and one input, it's clear how to compute the output. So you apply all of these weights, you apply all of these nonlinearities, and you get some output. This output is bad. You want to correct your weights, accordingly. You want to train your model. But you have an output. You can take derivative of this output with respect to the A of the last layer. It's computable. So we can compute the delta of this layer. You can propagate back this delta to previous layer, previous layer, previous layer. So delta of all layers can be computed. Having delta of all layers and knowing all z, because you do have z, because in the forward step you do have z's. Knowing all of these z's, you can compute the derivative of output with respect to all of the weights. Having derivative of output with respect to all of the weights, then you can do gradient descent. Basically, you can say, okay, any weight, any new weight is the old one minus some learning rate derivative of E with respect to that weight. And this derivative can be computed through this algorithm. This is called backpropagation. Any question? Okay, let me. Okay, so, these are steps of backpropagation. In backpropagation, as I explained, you start with applying a vector x as one of your data points to the feed-forward neural networks, and then you compute the output. It's quite easy to compute the output given weights and the input. You start with some random weights, and these random weights are usually close to 0. I will give you the reason later on. That's for regularization and avoid overfitting and problems. So you usually set some random weights close to 0, and then apply this vector x and vectors and compute all outputs. Basically, you have all A's, you have all Z's, and you have the output. Now, you can compute delta K because you know the output. Knowing delta K, you can compute any delta I for all of i's, which is less than K. For all K minus 1, basically the previous layer, layer K minus 1, layer K minus 2. For any layer, you can compute delta I. Because delta I is simply the derivative of the nonlinearity function that you apply to each perceptron, which could be logistic function, or could be hyperbolic, could be some many other type of nonlinearity. So that would be this nonlinearity summation of all of lambda j's, everything else. So it's a recursive formula which compute each lambda based on lambda of layer after that. So you have lambda k, you can compute k minus 1. Then you have k minus 1, you can compute k minus 2, and so on. So basically, you can compute all of the lambdas. Having all of the, deltas. Having all of the deltas, you can compute all of delta I ZLs. Each delta I ZL give you derivative of output with respect to UIL. This quantity is derivative of the output with respect to UIL. Having derivative of output with respect to UIL, you can update your weight. Okay, this is called backpropagation. So usually what we do is to start from the first data point and go to the last one, and then start again. So we have to go through all of the input in many cycles until the algorithm converges. And it's a very good practice if in each cycle you perturb your points randomly, you change the order, and avoid the case that you may get stuck in a periodical change of weights. So basically you feed all of the input data points and then you change the order of them and you feed them again and again and again until it converges. So what we use in practice is stochastic gradient descent. What I told you is gradient descent. Gradient descent is this, derivative of output with respect to the weight, okay? So what is a stochastic gradient descent? You know, if you have an objective function, that you can write this objective function as a summation of some elements. That's the case here. You know, you have this objective function, for example, and you can write this objective function as a summation of this objective function for every point. So summation of I to n of this objective function for each point would be summation for everything. So if you have an objective function which you can write it in this form as a summation, then gradient descent on weight w or variable w would be w minus learning rate over the derivative of phi. But since phi is summation of I to n, basically you can take the derivative inside and write it as derivative of, minus learning rate times summation of derivatives of I, right? In a stochastic gradient descent, for each data point, you compute the gradient at that single point. Instead of the summation, in a stochastic gradient descent, you just get rid of this summation. You compute the gradient at that single point. Okay? So that's pretty helpful in practice because this is going to be expensive. For every single point, if you want to compute the derivative with respect to the weight or your parameters, you have to go over this summation, which basically is derivative of this objective function with respect to all of the points. So instead of doing that, we take derivative with respect to the parameter for that single point that we are feeding to the network. It's called a stochastic gradient descent. So this is not the sigma, this is gradient at that point. In practice, actually, what we do is something between gradient descent and a stochastic gradient. A stochastic gradient descent is this derivative with respect to the parameters for all points. A stochastic is for single point. In practice, we do something in between, which is called batch gradient descent or mini batch gradient descent. So we don't compute this summation for all data points. We take a subset of data, we call it the batch, with size b, and then we compute this gradient for this batch of the data. This is the most common way of doing things, because if you do for a single point, it doesn't converge efficiently. If you compute it for all data points, it's expensive computationally. So something in between. Take a subset of points, a batch of points, and compute the gradient for that batch. Usually when people say that I use stochastic gradient descent, they mean batch stochastic gradient descent. Okay, that's the most common way of this. This is called, or mini batch gradient descent. Any question here? When you do mini batch gradient descent, the size of this batch would be a parameter. If you change this size, then the solution will change. Yes?
How long would it typically take to train your weights for a typical neural network?
Well, there is no typical neural network. It depends on how many nodes you have, right? In these days that we have deep network, and deep network basically is a neural network with many layers. There are models with millions of parameters or millions of weights. And it takes days and weeks on a machine with many GPUs to train the model. But if you have a neural network with one layer and 10 nodes, it takes a couple of seconds to train, or minutes to train. Okay, that's basically, an algorithmic form for mini batch stochastic gradient descent. And as I explained, you take a batch, say for example, the batch size here is 10, and then at each iteration, you compute the gradient for that 10 points instead of summing over all points. So another point is about learning rate. Yes?
For choosing your batch, is it, in that example, you chose every 10th point, equals 10. Is it customary to choose every however many points, or select data points randomly? Or?
Even here, I say here that, or in the previous slide, somewhere I say that try to permute points, don't choose the same 10 points every time. It's going to be random anyway, right? Yeah, you have to choose them randomly. You shouldn't choose every batch exactly the same in each iteration. So I talked about learning rate before when we learned about perceptron, that long learning rate means taking a big step toward the minimum in the direction of the minimum on the surface of gradient. And a small learning rate means take a small step. Small step means that it takes for a long time, it takes forever to converge. And large learning rate, what was wrong with large learning, huge learning rate or big value for learning rate? What was the problem that could happen in perceptron? Do you remember? Yes?
You don't converge.
Sorry?
You don't converge.
It doesn't converge, right? Why it doesn't converge?
So it overshoots the minimum.
Yeah, you may miss the minimum, it overshoots, instead of getting to minimum, the minimum is here, but you have a huge learning rate, so you don't get here. From here, you get here. And then from here, you get here. And from here, you get here. It never converges to the minimum because it's large. So in practice, these are like heuristic points, but people usually try this in learning, and it's quite helpful. They try to have source of adaptive learning rate, and this is a pretty common way to do this. Define your learning rate as a constant divided by t plus constant, another constant, when t is your iteration. Okay, in the first iteration, t is 1, and you have a large number for n. As you go on, t gets larger and larger, so n will be smaller and smaller, right? So you start with a large learning rate, but as you get closer to the solution, you make your learning rate smaller and smaller. So the assumption is that when I started with some random weight, I'm pretty far from the optimum point. So it doesn't matter if I take a big step, right? But later on, I'm close to the optimum value. So it's better to be careful and take like small steps. Don't overshoot, don't miss the minimum. Okay, any question? So the difference between neural network and deep neural network is that deep neural network is a neural network which is deep. Okay, so basically a deep neural network is a neural network with many layers. So when backpropagation introduced, we were not able to use backpropagation for deep networks. The reason is a phenomenon which is called vanishing gradient. When you take the gradient, when you have many layers, through this recursive formula, you take a gradient and you have to backpropagate it to all layers before that. At some point, this gradient gets vanished. It's so small that you cannot compute it anymore. It gets vanished. So you can't compute the gradient for if you have many layers. Okay? So we were not able to use backpropagation. So we were basically limited to neural networks with 1 hidden layer, 2 hidden layers, maximum 3 hidden layers. That was even rare, 3 hidden layers. So we couldn't compute it. And it's pretty well known that when you change the complexity of your network, you can change the complexity of your network with adding nodes in a layer or adding many layers. So if you add many nodes here, so it's going to be more complex model. But this complex model doesn't generalize well. It overfits the data. But when you add many layers, it predicts it generalizes better. It doesn't overfit. So that was our desire that we wanted to do. We wanted to have many layers, but we were not able to train it. Until 2006, that a paper was published in Science by Jeffrey Hinton. And Jeffrey Hinton was one of those researchers that first they was involved in introducing backpropagation, one of the people that reinvented maybe backpropagation. So in 2006, he had an idea published in Science, and the idea was based on a concept which is called restricted Boltzmann machine. Restricted Boltzmann machine is an unsupervised learning. Okay, so you don't need to know how restricted Boltzmann machine works. Just know that in restricted Boltzmann machine is completely unsupervised. You have a representation of data here in this node. In restricted Boltzmann machine, you can compute another representation of the data for these nodes. It's like PCA, for example, is unsupervised learning. You have a representation of data. You apply PCA, it gives you another representation of data, in another domain. Something like this. Restricted Boltzmann machine is like this. So suggestion of Hinton was that if you have a deep network, make your deep network in a way that each of these is a restricted Boltzmann machine. So I have input here, and I have output here. I can't apply backpropagation to this because of vanishing gradient. What I'm going to do is to take these 2 layers as a restricted Boltzmann machine and train this layer based on this one. Because I have this representation, I will find another representation here. Then I will take this layer and this next layer as a restricted Boltzmann machine and then compute the representation here. And I do this up to the end. So each layer will be learned based on the previous layer. So I have the weights for all layers, but it has been learned layer by layer. Now I apply backpropagation now and use these weights as seed weights. So I just need to do some fine tuning and adjust them. That was beginning of deep neural network. And that was 2006. It was, I think, 2012 that they in some competitions in object recognition, they had results way better than any other researcher in the world. So they beat everyone. So they got attention. And people started to seriously work on deep neural network. At the moment that we are talking, actually we can train very deep neural network using backpropagation and without this structure of restricted Boltzmann machine. So many things happen actually in this field that led us to do backpropagation for deep learning. So we are not done with neural network, get back to neural network later on, and we cover a convolutional neural network later on in the course, and we may talk about these techniques. But a very simple one is that people use to use a logistic function as nonlinearity. But now it's quite common to use this nonlinearity, which is called rectified unit. This nonlinearity, this is a nonlinear function instead of this one. But if you look at this one, you know, the gradient of this one is either 0 if you are in this region, or is 1 if you are in this region. So when you are taking gradient and going backward, your gradient is either 0, means that you knock down that node completely, or it's 1. If it's 1, it doesn't get vanished, right? You can propagate it back. It's not a small value. So that's one of the basically techniques to resolve this problem. And there are many other techniques. Any question here? Okay, we'll get back to regularization of these networks, how we can avoid overfitting, which is a part of complexity control. I just gave you, the general concept, and I told you about cross-validation. So we'll talk more about regularization of these neural networks, because it's quite important. These are models with many, many parameters. We need a way to avoid overfitting. So another type of neural network is radial basis neural network, or it's called RBN networks in short. Okay. What is called RBN neural network has a structure different from feed-forward neural network. The structure is that, as usual, we have d inputs for a vector of d dimension. Then I have m nodes here, but these m nodes are not perceptron. They are some nonlinear function. I call it phi. So for I phi 1 to phi m, I have m nonlinear function. So each data point will goes to one of these functions, and this will basically compute a nonlinearity for that particular point. Okay? And then as output, say I have y1 to yk, which is basically a linear sum of these outputs when some weights are applied. Okay, the output of this network, say for example y1, is going to be w11 phi 1, and suppose that I compute y1 for input, one of the input points x. That's going to be w11 phi 1x plus wm1 phi So it's going to be W11, W1, 21 for this one, W21 times phi 2x up to WM1 times phi mx. So the output is a weighted sum of these phi functions. Okay. These are called basis function, and since usually we use radial functions here, it's called radial basis functions. So yi is basically a linear sum of w like ji phi jx over all j. So as usual, our problem is to find parameters of the model that are these w's, with the assumption that these phi's are given, are fixed. I give you the nonlinearity phi, and you can compute phi of x. So the only unknown part is this parameters phi. The setting of the problem is clear. Okay. So I have x, which is d by n as usual, which is x1 to xn, and I have y, which is k by n, y1 to yn. Each of them is k-dimensional. Okay, so I can define, I have m phi, and each of these m phi's will be applied to x, and I have n x's. So in total, I have m times n numbers as the output of these functions when they applied to all of these endpoints. So let me define a function phi, a matrix phi, which is m by n. And this is, for example, is phi 1 applied to x1. And this is phi 2 applied to x1. And this is phi m applied to x1. And this is phi 1 applied to xn. And this is phi m applied to xn. So it's m by n matrix. And I define a matrix W and put all of these weights in it. How many weights do I have? How many weights do we have here? From phi to y. How many phi's do we have here? M. How many y's? So how many weights in total? mk, right? M times k. So it's going to be m by k. So this is W11 and this is W12. This W11 and this is W12 and this is W1k. Or put it the other way around. So k by m. So up to m, and here up to K. Okay. Okay, and this is my W matrix, right? So what's happening here is that my output is weighted sum of this phi's. I can simply write it as a matrix multiplication. I can say that the output Y is basically W transpose phi based on this notations. This is Y is a K by N matrix, and W is M by K, so W transpose will be K by M, and phi is M by N. So it's K by N. So I can write Y as W transpose phi. So basically, I put all of my unknown parameters in a matrix, and Y is known, and phi is also known, because I can, given form for phi, for this nonlinear function, I can compute this matrix. I can apply that phi to x1, I can apply it to xn, I can apply phi2 to x1, to xn, and so on. So I can form this phi matrix. I have Y, and my unknown is matrix W. So, and Y is W transpose phi. Now my problem is to find this W transpose, right? So my objective function would be Y minus W transpose phi squared when W is unknown. Okay, how can we compute this W now? Y is known and phi is known. W is unknown. Do you know this problem? Do you know this optimization? Should I take derivative and do a stochastic gradient descent? No? So what is the solution? What is the solution? It is least square problem, isn't it? So it has closed form solution. So this norm is basically a trace of Y minus W transpose phi transpose times Y minus W transpose phi. Which is trace of Y transpose Y plus this term is squared, which is phi transpose W, W transpose phi, minus 2 phi transpose W, Y, when you expand it. And then if you take derivative of this trace with respect to your parameters W, then the first term is 0. Then you have phi transpose W, W transpose phi. Take derivative with respect to W. It's quadratic, so it's going to be phi transpose W. It's very easy to make mistakes in terms of transpose. Is this the derivative or the transpose of this the derivative? So there is a matrix manual. The link is on my webpage, and then you can check and make sure that all cases are there. Derivative of trace with respect, in linear form, quadratic form, cubic form, derivative of determinant, derivative of with respect to vector, with respect to matrix, with respect to transpose of a vector, transpose of a matrix. So for your assignment, it's going to be pretty handy. Just refer to that one. So make sure that you don't make mistake, and I hope I didn't make mistake here. But we'll see. If I made a mistake, the dimensionality will not match, and we'll see that. So this is a linear. So derivative would be phi w. Phi y transpose. Derivative with respect to w would be phi y transpose or y transpose. Phi, I think it's phi y transpose. So this derivative, you need to set it to 0. And this one has 2 as well, because that was quadratic. So it means phi transpose w is phi y transpose. So it means w is phi transpose inverse, multiply the inverse from both sides, phi y transpose. That's your w. And then y is w transpose phi. So my estimate, or y hat, is w transpose, means transpose of this, which is y, phi transpose, phi transpose inverse, transpose, which would be the same, times phi. Okay. It would be something in this form, or maybe the transpose of this times y. So you have to look at this matrix manual to make sure that the transpose is correct. I think it should be, y should appear on this side. In terms of dimensionality, it makes more sense because, this phi is m by n, so it's going to be m by n. The transpose would be n by m, so it's m by m. And this is m by n. This is n by m. So the whole thing would be n by n. And y is k by n. So I think you have a y transpose here, which is n by k, and everything is this transpose, which is n by k. Yeah, it should have this form. So anyway, this is noun. It's in terms of phi, you can compute it, and y transpose is noun, your input. So you know what the output of the model is based on these weights. So you can compute it in closed form. So RBF has a solution in closed form. So what happens actually is that we are mapping the data to a new space. These phi's compute a new basis, and then we do a linear function in this new basis, on this new basis. And this linear function on the new basis would be nonlinear on the original sense. Do you remember the trick that we used for LDA to make it quadratic? Told you that you can augment your input space and then apply a linear function to that, and it becomes quadratic or cubic. That's exactly the same thing. When you're augmenting your input, or you're applying some nonlinearity to your input, so you have a linear function on some basis, but it's nonlinear on the original step. If you think Fourier transforms have this form, except that this phi is just sine and cosine, right? Wavelet has this form, except that these phi's are some other bases based on wavelet. So basically, we can compute our data in some basis and then do a linear function in that base. So that's radial basis function, which has closed form solution. Any question here? Okay. So we started with classification. We started with Bayes' rule, and we got to some models that seems have no connection with Bayes' rule that we started from. Well, let me show you the connections now, and show you that here actually we are somehow approximating the Bayes classifier in some weird way with some functions. But before I do this, I have X as my observations, and I have Y as a label that I want to compute. Okay? I'm not sure if you're familiar with notations of graphical model, but these are notations of like BaseNet. Graphical model, directed graphs. Here, actually, I'm presenting a joint distribution of X and Y. The only thing that these arrows and this basically circles tell me, these are two random variables, is that this joint probability between Y and X can be decomposed this way. It's P of child given parent, Px given Y, times Py, which is basically Pxy. But if I show the model this way, it means that, again, child given parent, it's P Y given X times Px. Again, this is Pxy. But here, I'm expressing that Pxy, the joint probability, can be decomposed this way. And here, I would say that this joint probability can be decomposed this way. So let's start with the first model that we had, LDA. Do you think LDA was this model or this model? Or let me first ask you another question. One of these two models is called generative model. The other one is called discriminative model. And it's a pretty general term. You can see it. It's not just about LDA or logistic regression or class. In general, you can see in the literature that say this model is a generative model or this model is a discriminative model. Do you know the difference between these two? Okay, we are almost out of time, and we'll discuss this in the next lecture. But very briefly, generative model means that you can generate data. If you look at this model, you can generate data. Think about, suppose that you have two classes, and one class, the label of one class is 1, the label of the other class is 0. In LDA, for example, we modeled our observation as a Gaussian. It's a generative model in the sense that if I tell you the label, if I give you y, say I'm in class 1, then you know which Gaussian you can sample from. So it can generate a new data from that class. This is a generative model. But this one is not. Right? I never model px given y here. I model py given x. So if you tell me what the y is, I don't have distribution or x to sample from. This is not generative. I can do classification, but it's not generative. I cannot generate new points. So we'll talk about this in the relation of this RBF neural network with the Bayes rule. Any question? It is in the web page, but if you haven't seen that, I have office hours tomorrow from 9 to 10.